So in this set of videos, we're going to talk about how electrons do something called hybridize to try to explain what electrons are doing in a bond. And I want this may sound a little wacky once we get started. I want to start with a quote from a theoretical chemist from the University of Oxford in England. His name is C.A. Coulson. And he wrote in 2007, this was published in Chemical Engineering News, that this is his quote. So here is his quote. "Sometimes it seems to me that a bond between atoms has become so real, so tangible, so friendly, that I can almost see it. Then I awake with a little shock, for a chemical bond is not a real thing. It does not exist. No one has ever seen it. No one ever can. It is a figment of our own imagination." And that doesn't really mean it doesn't exist, but no one has ever seen it. So what we're trying to do with what we've been talking about and what we will talk about in these videos is describe a theory or a model that explains how molecules behave and what we observe with our experiments. So just keep that in mind as we go forward. So as we've talked about, covalent bonding is formed by the sharing of electrons of atoms that are next to each other so they can share electrons. This can only really happen when the orbitals that have those electrons overlap. So this is an example of hydrogen chloride. Hydrogen has a 1s orbital with one electron in it. The orbital that is holding the electrons that are bonding for the chloride are in the 3p, because chlorine, let's get a pen, this is the chlorine's valence structure. Whoa. This is chlorine's valence structure. This is chlorine's electron structure. This is his valence structure. This is where it needs the extra electron. The 3p5 has 5 electrons. It needs one more. So that's the one that's going to overlap. You can see over here, this is showing a Cl2 bond. For Cl2, this would be HCl. This is a picture of H2. Here you have 2p orbitals overlapping. When atoms come together to bond, their nuclei get closer and electrons get closer and closer together, so that you're increasing the attraction between the nucleus of one atom and the electron of another, until you get to the point where if you get any closer, that would be right here, the two nucleuses would start to repel each other. And then that's as close as you can get, because if you bring these two any closer, these two nuclei will repel. So this is the lowest, this distance apart is the point of lowest energy for these two atoms being bonded. It's the most stable for this bond. But we need to find a way to explain the geometries that we believe exist of these molecules, that explain the geometries in a way that is consistent with these orbitals overlapping, and that's what we're going to try to do right now. So we're going to think about carbon. Down here we have carbon's valence structure. Its valence structure is 2s2, 2p2. So carbon, in this structure, when it's just in its ground state, it only has 2p electrons to share and to bond. But we know that often carbon forms 4 bonds. 4 equal bonds. In methane, it has 4 equal bonds with 4 hydrogens. That's a tetrahedral structure. If carbon absorbs a small amount of energy so that it can promote these two electrons from the 2s, or at least one of them, into the 2p, then it would have 4 unpaired electrons. 1 would be a 2s, and 3 would be in the 2p. So if this was to overlap with something, and these 3 were overlap, you could get 4 bonds, but they wouldn't all be the same, because the s is different from the p. And we know that carbon forms 4 equal bonds with 4 equal bonds. So therefore it has to form bonds with 4 equal orbitals that are overlapping. The way we explain that is to say that this 2s is going to hybridize with this 2p to form 4 orbitals that are capable of bonding, but we're going to give each of those orbital a new name now when they bond. We're going to call it sp3. And this sp3 just comes from This S and these 3 P's, we put them together, 1s, 3 P's. If they hybridize, and the word hybrid or hybridize means to change, it means to crossbreed. So let's find a better definition. So a hybrid, and you should have seen this in biology, is a blend of 2 different things. It's a new thing that blends the characteristics of 2 things. And that's what we're doing with this new orbital. We're blending the characteristics of the s orbital and the p orbitals into one type of orbital. Since we had 1 s and 3 p's, we now have 4, 1 plus 3, of these new orbitals. Depending on how many of each type of an orbital an atom has, it will have a different hybridization. You find out the type of hybridization it has from the sum of the s, p, and d orbitals that the atoms that are bonding have. So for example, AX2 would have an sp hybridization. So AX2, so I don't think, we're going to come back to this, okay, because the way it's written I don't think it's particularly helpful. What it's trying to tell you is if you have something AX2, so we would let's take SO2 as an example. Actually, depends on the lone pairs. We're just going to ignore this for right now, okay? It's confusing. Okay, so when we're thinking about hybrids, we're thinking about one atom that's it's changing its orbitals so it can form equal types of bonds all around it. So let's think of beryllium right now. Beryllium, which is in group 2. So ordinarily the valence structure of beryllium, I hope, is 2s2, which means beryllium has a complete s shell. But let's say beryllium wants to bond. What's it going to do? It doesn't need any more electrons in that s shell. So it has 2s2. Is it 1s2? No, it's 2s2. 2s2. Let's cross this out for a second. And then, oh, blah, 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 blah. Let's do it here. We have 2s, where it had the 2 electrons. This is before it's bonded. When it's all alone, it just has 2 electrons in its 2s shell. Now it wants to bond. So it's going to promote one of these electrons to a 2p orbital. Okay, that means that now it has 1 electron in the 2s and 1 in the 2p. This makes it available if it wants to bond. If something else over here has a few electrons that can bond, one of them could go here and one of them could go here. And then you'd have 2 bonds. But they would be 2 different bonds because this would be bonding with the 2s and this would be bonding with the 2p. And when beryllium forms a bond, it's going to have equal bonds around it. They won't be different if they're not double bonds. So we need to find a way to have this bond be the same as this bond. That's where hybridization for beryllium comes in. We're going to combine the shape of the 2s and the shape of the 2p, or the character of the 2s with the character of the 2p, so that what beryllium's really going to be offering when it goes bonding is 2 hybridized orbitals. So instead of 1 2s and 1 2p, what it's going to bring to the table is, well, we could call it a 2sp, but we don't put the energy level in there. It's just an S2 2sp orbitals. That's what it's going to be offering its friends when it goes to bond, and it can form 2 bonds. So let's look on the next page and see how that would work out for beryllium. Okay, so beryllium, when it was all alone as a single atom, not bonded, it had 2 electrons in its 2s orbital. Not particularly stable because it only had 2 electrons in its outer octet, but at least that orbital was full. But it doesn't have an octet of electrons, so it's not particularly stable, so it bonds. So in order to have equal bonds around it, because, and this here, down here, we're making a picture of beryllium fluoride. In order to have equal bonds, and again, we're assuming this, I suppose, would be a covalent bond, so it would be beryllium difluoride. I'm not right. That's what we're going with right now anyway. Because these would be covalent bonds, so they'd be shared. So that these 2 bonds would be equivalent in nature, equivalent character, equivalent length, we're going to, if it just promotes 1 electron into 2p, it could make 2 bonds with the fluoride, but they would be different. So we're going to combine the character of the 2s and the character of the 2p, and we're going to make 2 bonds, but we're going to call them each an sp orbital, instead of one being an s and one being a p. So now we can make 2 bonds. Beryllium would have 1 electron here, 1 electron here. Fluorine will put one here and one here, and each bond will have the same character. And what fluorine brings to the table here, it needs one electron in its p orbital, so fluorine isn't hybridizing right now. Okay, fluorine's just offering its p orbital. The hybridization is happening around beryllium. So having beryllium have two equivalent orbitals, this would be an sp, and this would be an sp, that's consistent with the geometry of this compound, which is linear. It has two equivalent orbitals around this central beryllium atom. So if a central atom contributes an s orbital and two unfilled and two p orbitals, if it contributes an s orbital and two p orbitals that have electrons in them, these three would hybridize. They would combine to make new orbitals that have the characteristics of each. And because there's three of them combining, we'll get three when they come out. Three babies. And each baby will be have some s characteristics and some p characteristics, but we're going to call these babies sp2 orbitals because they're made from one s and two p's. Remember in the previous one, we called them sp orbitals because these babies were made from one s and one p. These are made from two p's, so the babies that they make are called sp2. And there are three of them, so that the number of possible hybrid orbitals you have is the sum of the number of s's and the number of p's that have electrons in them to begin with. If this seems a little weird, remember I said at the beginning there was a theoretical chemist who's some guy with a lot of education saying that bonding is weird, it's a figment of our imagination. So it's weird for him too. Again, we are trying to think about how electrons are acting at the electron level, which is beyond the microscopic and the nanoscopic level. And things down there are not the same as they are up here. And some of this is we're coming up with theories and models to explain how we see molecules behave. And we see them, for example, with the BEF2 that I talked about a couple of slides ago. We see that as a linear shape. So we're trying to have an explanation of the bonding in there and the electrons that is consistent with everything that we know so far. If we have a central atom that, I don't like this word degenerate, I'm crossing it out, I don't know what it means. We'll use make. If we have a central atom that around it has four orbitals that have electrons in them, filled or unfilled, in its valence shell, so a central atom that has a s orbital with some electrons in its valence shell and three p orbitals that have electrons in its valence shell, these will hybridize to make babies. And the babies that come out will have some S character and some P character, and they're going to have more P character because they're being made by more P daddies. So each one we would call sp3. And there are four of them because we're making them from one S and one S plus three Ps. This is how you get a tetrahedral, because here you have four equivalent bonds, and when these bonding electron areas want to be as far apart as from each other, they form a tetrahedral in space. Okay, we're going to do two examples and then keep this video short, and then do another video. So we're going to determine the hybridization of bonds for the central atom in the NH2 ion. This is NH2 minus 1. That's what this is, minus 1. So first we have to draw the Lewis structure before we can determine the hybridization. Nitrogen has 5 valence electrons, and hydrogen has 1, and we have 2 hydrogens. So that gives us a total of 7, and we have 1 extra electron because this is an ion. So we have a total of 8 electrons. So I'm going to put my nitrogen there. I'm going to put 2 hydrogens around it. I'm going to put 2 lone pairs here. That gives me 1, 2, 3, 4, 5, 6, 7, 8 electrons. I have 0 formal charge on my hydrogen because the formal charge for hydrogen is 1 valence electron, and I've assigned 1 electron to it. I have a 0 formal charge on this one. My nitrogen has a formal charge of -1 because its valence electrons are 5, and I've assigned 6 to it. 1, 2, 3, 4, and then half of this, 5, 6, giving me assigned electrons of 6, which gives it a -1 charge, which is appropriate because this is an ion with a -1. And the formal charges have to add up to the charge on the ion if it's an ion. So now we have a Lewis structure. So now let's determine our geometry, which I suppose I could have determined even without drawing it. We'll see if it's consistent. We'll see if our hybridization is consistent with the shape of this. From the Lewis structure, what would you say the shape of this would be? Well, the Lewis structure, the geometry of this should be bent. I should have drawn it like this, with the pair here, and the pair here, and the H here, and the H here. Now let's determine our hybridization, because that was the point. Okay, so nitrogen, the valence structure of nitrogen is S2P3. It has an s orbital in its valence shell, and it has 1 electron in each of its p's. Px, py, pz. Okay, that means it's contributing. When we talk about hybridization, we're talking about hybridization around the central atom. So that's what we're thinking about. Nitrogen's the central atom. It's contributing an s orbital to its hybridization and 3 p orbitals. So we have to make this s and these 3 p's have 4 babies, because there's 4 of them all together, that are all the same. So we're going to make them all be the same, we're going to call them sp3. We're going to draw 4 sp3 babies. Why is it P3? It's P3 because P3, there were 3 P's that were contributing. Now, what's going to be filled in here? Well, we have 1, 2, 3, 4, 5, 6 electrons. I can't count today, can I? How many did we have? It's an ion. So we have 1, 2, 3, 4, and we have an extra electron, which I'll draw in blue up here because it's a -1 ion. So I have 1, 2, 3, 4, 5, 6 electrons. So I'm going to put 1, 2, 3, 4, 5, 6. That shows me I'm going to have 2 lone pairs, which I do have, and I have 2 orbitals that are available for bonding, which is what we have here. The shape of sp3, the family, is tetrahedral because you have 4 orbitals that will be equally spaced. If you go back to your sheet that I gave you with the different geometries, you'll see the tetrahedral family will always be formed by the s3 hybrid orbitals. So in reality, if you memorize that, it makes things a lot easier.